Hello, everybody. Mr. Hennon here for a little discussion on angular versus tangential variables. So as we deal with this rotational motion stuff, we want to kind of understand that just because you're rotating around the circle doesn't mean you're not also moving with some kind of tangential motion. For example, if you've ever talked about people skating and they crack the whip, and the reason why that person at the end of that skate of group of people that crack the whip is going to be the most likely to kind of fall off is because of how fast they're going. So when I talk about the person in the middle, they're basically stationary. They're our pivot. But as I look at this, all of these are at the exact same angle. So the angle is the same, but this person has to travel this greater distance than this person, than this person, than this person, and so forth. So what you find is your tangential speed or your tangential velocity at the very end is going to be greater, even though you're following the same angular speed. Interesting concept. So as we kind of relate that, we know that tangential speed would be the arc length divided by time. That's just going to be r times theta, but theta over t is our angular speed. So what we end up with is a neat little equation for finding the tangential speed or the tangential velocity, but mostly we're just dealing with speed here, is based off of the radius multiplied by your radians per second. So this is why if you will go through a larger circle, you're going to have a greater speed. We can even continue this and talk about the fact that they're going to accelerate. They're going to actually have a tangential acceleration. As they go from here up to there, they're speeding up. They went from rest to suddenly they're moving. Same situation. As you kind of tweak everything, we know tangential speed, initial and final. That's just going to be r omega, and then you pull those out. I usually write this as omega f and omega I, same general idea. But the main thing is your tangential acceleration is just the radius times your angular acceleration. So that's kind of neat that they both come out that way. So let's take a look at a little example. We've got a helicopter blade. It has an angular speed of 6.5 revolutions per second, an angular acceleration of 1.3 revolutions per second squared. For point number one, so look at point number one right there, find the magnitude of the tangential speed and the tangential acceleration. The first thing is we have to have our speeds and acceleration in radians per second. So if I am given something like 6.5 revolutions per second, we know that there are 2 pi radians in one revolution. So we're always going to get rid of revolutions and basically multiply by 2 pi to get that. So 6.5 times 2 is going to be 13. I'm just going to write this right now as 13 pi radians per second. I know that technically that would not be the best answer because I don't like to leave it in terms of radians. The same thing is true here. We need to change this into radians per second squared. So I'm basically going to take 1.3 and multiply by 2 pi. So that's going to be 2.6 pi radians per second squared. And so as I'm trying to figure this out, all we have to figure out is how far it is from the pivot point out to this. So this would be our radius, and they tell us that that is 3 meters. So to find the tangential speed, we would just take 3 and multiply by this number, or 3 and multiply by this number as we do those two. And so we've got that 6.5 times this. That gives us 40.8 radians per second. To find that, we should be able to kind of calculate everything out. This is actually incorrect. This should not be the alpha. This should be omega. Apologize for that. So we just plug that number in. 3 times that gives us 122 meters per second. Pretty amazing. And then the same thing with our alpha. We convert that into radians per second squared. Your tangential is r times alpha, and then 24.5. So we're doing about 2.5 G's as we're going around that circle. So just some neat little stuff. However, I know if I am going around in a circle or rotating, I also am going to have a centripetal acceleration, something that's pulling me towards the center. Actually, if I look at anything going around in a circle, it has two kinds. It has centripetal acceleration down here, Sorry for that. Sometimes the pen forgets that I want to actually use it. Let's go backwards for a second. And I get my pin back. So I am always going to have a tangential that's going to be toward the center, and then I might have a our tangential acceleration that would be in the direction of its motion, and then a centripetal that's going to be toward the center. So the true acceleration of this is going to be kind of this diagonal. To find centripetal acceleration, we know that it's normally v squared over r. So if I plug in r omega and that's squared, that's going to be r squared omega squared divided by r gives me an r omega squared. So this is another way of finding the acceleration. We have two different kinds. So we've got our omega multiplied by r is going to give us our tangential speed. We have r times the alpha, which is going to give us our tangential acceleration. And now we have r times omega squared, which is going to give us our centripetal acceleration. So put all those lovely equations together. Oops, got to move out of the way again. Maybe I could be the person that's up here throwing the discus. So starting from rest, the throw accelerates the discus to a final angular speed of 15 meters per second or radians per second. And in a time of 0.27 before releasing it, during the acceleration, the discus moves in a circular arc of radius blank. Find the magnitude of the total acceleration. So in this particular problem, what we're actually going to find is we're going to find the tangential acceleration and the centripetal acceleration, and then they are going to be the two sides of a right triangle. So basically my acceleration squared would be the tangential acceleration squared plus my centripetal acceleration squared. So as I do that, I just have to go into how do I find each one of those lovely bits of information. So my centripetal is just going to be the radius multiplied by, hate that when it doesn't like my pen, it's just going to be the radius multiplied by my um, angular velocity squared. And then to find the tangential, I have to actually find the acceleration. So it goes from 0 up to 15 radians per second in 0.27 seconds. So this is the acceleration of it, angular acceleration, and then multiply that. So now I have those. And then, like I said, I'm just going to use Pythagorean theorem and find that acceleration. So neat little problem with you're talking about throwing a discus. Here's the last part. I think this is kind of cool. So if you think about a wheel going around in a circle as it's basically it's rotating as you drive down the road, that wheel should be related to how fast you're driving down the road, shouldn't it? And here's the cool part. If I actually talk about a arc length around that circle, that's also how much I'm moving horizontally. So if this goes from point A so that point B is at the bottom, so basically this wheel is rotating over, what we find is the distance I move is equal to the arc length. Well, wait a second. If the distance is equal to the arc length, maybe we can kind of relate them together and get some kind of relationship here. And what you will find, sorry, didn't mean to go past this, my pin back, is that the linear speed is still equal to r times omega because this distance, this arc length divided by time would still be equal to r times theta over time. And look at that, that's still my omega. The same thing with my acceleration. So the same equations that we have for a point on the outside, like how fast it's moving in a tangential motion, is also how fast this car is driving down the road. So these two velocities are actually the same. They're found exactly the same way, which I think is kind of neat. So if a car goes from 0 to 60 or something like that in a certain amount of time, we can also figure out how much it rotates. So for example, if I start from rest, the car accelerates for 20 seconds, constant linear acceleration of 0.8 meters per second. The radius of the tire is this much. What angle through which each wheel has actually rotated? So as I kind of go about this, the first thing I can actually figure out, I have the linear acceleration, I have that. I should be able to actually figure out their linear speed. So if I can figure out their linear speed at the end of it, I should be able to relate it. But I don't have to. I can go about finding the angle by saying that the initial angular velocity multiplied by time plus 1/2 my angular acceleration multiplied by time squared. Well, this is 0 because it starts from rest. You go, but wait a second, I don't know what that acceleration is. But the cool part is my theta would equal 1/2. For this, I can put in that it would be the radius of the circle times the acceleration of the object and then multiplied by time squared. So I end up with rat. And that should tell me how many radians this thing has gone through. And when I plug everything in, there's my angular acceleration. They did it that way. I don't think you even need to. We can just kind of realize that when we calculate this, we can kind of figure that out and then ka-chunk everything together, and we've got all of our information. So we're good to go. I don't know why they have a little square on here. This square should not be there. I'm going to cross that one out. We're basically just taking our acceleration and multiplying by theta. I'm not worried so much about rotation in the clockwise versus counterclockwise direction. The reason why they put positive and negative signs on there is the fact that if it rotates clockwise, that's going to be one direction. If it's rotating counterclockwise, that's another direction. We have a little bit of that, but I'm not worrying as much of changing that direction as we kind of go through there. Hope you enjoyed this little bit on how we go from our rotational motion into linear motion, how they're still related to each other. Take care.